Hi, so welcome to sunny San Diego and TSC 2017. I can assure you it does get sunny here, and in fact, that we were all in bikinis on December the 15th. And now I put a really horrible image into your heads, haven't I? No, not me, right? Not me. Anyway, so I think we live in very exciting times for this discussion of sort of consciousness and AI, because we're getting to the point where computers are getting more powerful enough that they can start to maybe pass the Turing test and give us some run for our money as human beings. Some people find that a bit scary. Some people find it very exciting, and it will change everyone's lives. It will certainly change everyone's lives. Let's hope all for the better. Generally, scientific change has improved our lives over the years and not been a disadvantage. So I think many of the very negative things that we see, mainly coming out of Hollywood, are a bit too negative. So we have three speakers today. The first one is Roger Penrose. Roger Penrose got Stuart and I both interested in consciousness many years ago when he wrote his book, The Emperor's New Mind. And Roger is going to explain to us how he thinks that humans have a different type of intelligence than machines, and that maybe it's a quantum gravity computer. Our second speaker is Yosha Bark. He thinks that computers indeed could be conscious, and sees no reason why not, and indeed will explain to us the theory by which they would achieve that sort of consciousness. And our third speaker is Harman Nevin from Google, and he is building the world's most powerful computers, or at least they hopefully will be the most powerful computers in a few years' time when he perfects all of the things. So quantum computers, not the quantum gravity computers that Roger is saying that we need, but at least quantum computers. And he's going to explain to us how quantum computers work and how far they've got with building a quantum computer. A very fascinating talk and a very fascinating guy. So I won't talk any further because I'll use up valuable real speaker time. Let's have Roger Penrose up to the stand for this first speech. Thank you very much. Thank you.
Well, it's a great pleasure and an honor for me to be able to address this meeting, and I want to present the point of view that I've had for some while, although modified in various ways, which is that consciousness is not the result of computation, it's something else. Let's see if I can get this thing to work here. This old-fashioned technique, I'm afraid. I can't read what I've written, unfortunately, because my eyesight has deteriorated somewhat, but I hope you can. I can get the gist of what I said, and that is, well, consciousness, there are many aspects to consciousness, and people often refer to many of them like things that we feel, which might be pain, or which might be the appreciation of beauty, or love, or a color, or something like that, and the experience that we have. However, what I want to say is something very, very specific. And the argument is that if this very specific thing is something that can be shown to be not a computational thing, then this raises the question of whether these other qualities could ever be explained. In fact, it's more improbable in a way that the perception of the color blue, for example, is a computation than the things I'm going to talk about, because I will talk about mathematical things, and people tend to think mathematical things, oh, well, that must be computational. So I want to try and explain why that's not the case, and why understanding, I want to concentrate on understanding. I mean, of course, as I say, that is a very limited aspect, if you like, of what consciousness is, because we can be conscious of all sorts of things without understanding them. But understanding, I claim, is something which is demonstrably not the result of a computation. Of course, even in the way we use computers, the way we use computers is to do complicated calculations. The computer doesn't know what it's doing. It doesn't understand anything that it's doing. And I can illustrate that a bit more in what I want to say in a moment. But we have to present the understanding which tells us what computation to do and what the computation means in the end. So from that point of view, it's something rather different. Now, I'm not sure I can see. That's the trouble with this system. I can't see what I'm doing here. Let me move this so I hope you can see the whole transparency. I think you can. Okay, I think perhaps I've covered what's on that, so let me move on. Let me give you an example. This is one I made up recently it's a chess position, and it's an example which is stimulated by an example which was made up a long time ago. But let me give you this one. So long as you understand the rules of chess, you will see this is a rather strange position. Black has an enormous advantage. You see queens and rooks and bishops and things. You might worry about all those bishops being on the same color. It's not an illegal position because the two of the bishops were bishoped by pawns. You see, you can move the pawn up to the end of and change them into a bishop. That's perfectly legal. And they're also on the same color, which you might worry about that, but that's perfectly legal again. So the position is a genuine one, and it's easy to see that it's a draw, because the black pieces here are all trapped by the barriers of pawns. They can't move if white leaves them alone. They're completely trapped, and the bishops can't do anything because the barrier is impervious to the bishops. They're on the wrong color. So it's obvious, if you know much about chess, that this can't be won by black. But if you show this to any of these very high-powered chess-playing computers, these will say that it's a win for black, and that you can see it's completely wrong. In fact, I think some of these will actually, because there's a rule about a draw, if you go on and on and on without a piece being taken or a pawn moved, and if you do that for 50 moves, then it's announced as a draw. Now, the thing is here that what black may, according to one of these chess-playing machines, the black starts sacrificing these bishops, which is ridiculous to do, of course, because it thinks that it doesn't want to draw because it's a win, you see, but it's not. And so all you have to do is move the king up to here, and then you checkmate in a couple of moves. So that's a stupid thing to do. So what I'm saying is that the little bit of understanding of what the game is about can get this particular position right, even though what's going wrong now? Okay. Anyway, it just shows that a little bit of understanding in certain circumstances it can defeat what a very, very powerful computer can do, which could defeat almost defeat or at least draw with any human. So let me move on. This is just to demonstrate that there's something a bit different about human understanding and simply computing. Of course, you could put rules like that into your program and make it make the right answer for those positions. But that's being wise after the event. Now, of course, you could argue that chess is a finite game, and so no matter how clever your position is, if you had a powerful enough computer, it could simply work the whole thing out to the end. This isn't a very good system, is it? Can this be made more horizontal or not? Yeah, that's better, thank you. Right. Just leave that down there. Oh, okay. Anyway, so what about the infinite? And this is where you start to see real differences. Now, you might say we can't think about infinity. That's completely wrong. For example, you could think about the statement, if you add two odd numbers together, you always get an even number. Now, that's a statement about an infinite number of things, and it's very, very easy to appreciate. You don't have to think very hard to realize that's true for all numbers, and for all numbers, that's an infinite number of numbers. So in mathematics, there's no real problem about thinking about infinity. However, the rules that you use to talk about infinity, that's where you can raise the question about the difference between understanding and pure computation. Again, I can't see what I've written here, so let's not worry. I hope it's on there, whatever I want to say. Now, let me explain how one often deals with the infinite in mathematics. Actually, some of these I may need back again, so I'm not quite sure what to do. Here we go. This is one of the ways that one learns at school about how to deal with the infinite. Suppose you had a proposition which depends on a natural number. When I say a natural number, I mean 0, 1, 2, 3, 4, a whole number, a non-negative whole number. Now, if you want to have a proposition which depends on a number n, a natural number n, how would you prove that that's true without running through all possible n's? Well, the standard way of doing it is to prove it's true for 0, and then prove that if it's true for n, then it's true for n plus 1. For some particular n, then it's true for that particular n plus 1. And that is what's called mathematical induction. Now, that's an example of something you could put on a computer. So you could put that rule on a computer. That's fun. And you could put all sorts of other rules on a computer. What I want to show is that rules... actually, can I keep that one there, or is it going to flop off like the others? There's a very famous theorem, and my position on this was very much influenced when I was a graduate student at Cambridge, and I went to various things which weren't at all what I was doing. One of them was a course on mathematical logic, and I learnt about the Gödel theorem, and I'd previously thought, well, the Gödel theorem says you can't prove certain things in mathematics, and I didn't like that idea. But that's not what it says. So what it says is described here, and again, I'm afraid I can't read it, but never mind. Is if you're given a system of theorem-proving rules. Let's talk about theorems in mathematics about natural numbers. There could be things like Fermat's last theorem that Andrew Wiles proved a few years ago, or it could be the Goldbach conjecture, which is still unproved. That is that every even number greater than 2 is the sum of 2 prime numbers. A very simple thing to state, but nobody knows for sure if it's true. It probably is true, but nobody has a proof of it. But the way you could prove these things is have a system of definite rules. And these rules would give you a proof. Now, I'm calling the rules R, and the thing is that if you want to use the rules, you've got to believe that the rules don't give you nonsense, like 2 equals 3. That, of course, would be an example of an inconsistency. Now, the famous Gödel theorem, what Gödel showed, was that if you have rules which are checkable by a computer, so that is to say, if you have what you claim to be a correct application of these rules, and a computer can then check to see if that's true or not. So that's the kind of rules I'm talking about. So I should have said that this is not just Gödel's theorem, but it's the Turing version of Gödel's theorem. I think I want you to hold these things too, if you could. So let me see if I can find this. Yeah, hold all that. Thank you. Yes, so this is the Turing version of Gödel's theorem, which is actually a lot easier to prove than the original Gödel theorem. The Gödel theorem was horrible to prove. But the point about this, no, don't take it away. The point about this, is it in the right place?
I'll fix it.
Oh, it's not in the right place. Oh, it should be in the right place. It should be lined up right. Okay, thank you. Yeah. So what Gödel shows is that for any system of computational rules of proof, you can construct a particular statement about numbers, and this is what I call G of R, the Gödel statement of R, which has the strange property that, first of all, it's true, and secondly, it is not derivable by means of the rules. Now, how do you know it's true? Well, because it states something about the rules that you have to trust if you're going to use the rules. Now, you see, the rules, if you're going to use them and believe the results, you've got to believe that the rules only give you truths and don't enable you to prove 2 equals 3. So those rules have to be, well, they have to be consistent. If they were inconsistent, then you could prove 2 equals 3. So they have to be consistent, and let's say they have to be sound, which is the word logicians use for, they have to give you only right results. So as long as you have that faith in the rules, if you're allowed to use the rules and believe that using them gives you the right answer, then you must know that G of R is true. However, it's not derivable using the rules. So it's your understanding of why the rules work allows you to transcend the rules. So the rules, whatever they are, aren't good enough to prove G of R, yet your understanding of what the rules do does tell you that G of R is true. So we've somehow transcended the rules by our use of understanding. And now an interesting point here is you've got to understand what G of R means. And meaning is an essential feature here. See, what people don't think is, well, what's meaning? You just use the rules and it doesn't matter. And often in mathematics, you have systems where you're not interested in what the symbols mean, you're just interested in the rules. That's fine. That gives you a useful kind of area, like group theory and things like that. But for this particular case, you really need to know what the elements that the rules are operating on are. And what these elements are natural numbers, 0, 1, 2, 3, 4, etc. And there are other systems where you have funny kind of numbers where the G of R wouldn't be true. So it really does depend on your understanding what the operations, what the things are you're operating on, what the things mean. And the meaning is something which is not encapsulated by the rules. And it's an important point that meaning is something different. Okay, well, what this basically tells you is that our understanding is not rule-driven. It's not a computational thing, but it's something we do in our heads, and it's something that enables us not just to do things like this, but to write computer programs and make them do what we want. And we know they do what we want because we understand what the operations are. So that's the way computers are used and so on. Well, I want to show you, see, what this tells me is that what is actually going on in our heads is not rule-driven. It's not algorithmic. There's something else. Now, you see, the laws of physics, I wasn't quite sure which order I would do this in. Let me do it here. I'm going to talk about, you see, I've just been talking about, yeah, maybe I'll take this. It's helpful, thank you. I've just been talking about mathematics, you see. And I said at the beginning that mathematical understanding is something very limited. You could understand lots of other things. What about understanding in general? Well, I'm saying if mathematics understanding, you might think this is the most likely to be something you put on a computer. But that's, on the other hand, it's the thing you clearly can't put on a computer. That's well-established piece of mathematics, that mathematics itself, there are many things in mathematics which are not computational. And I'll give you an example in just a minute. But what about other forms of consciousness? Well, conscious understanding, or what about consciousness? Human understanding is what I said. Human consciousness, animals. I would certainly believe that at least many animals have consciousness. I'm sure there are enough like us. People talk about their dogs and believe that they're conscious. I think it's absolutely right. Squirrels, I would think that birds are conscious, all sorts of things. But I don't know how far down it goes. What about life? Well, I think not all life is conscious, but there is a line between what's conscious and what isn't. And what I am saying, that conscious things are making use of something that unconscious things aren't. Do we have a problem? Okay. Now, I don't believe that our consciousness is some mystical thing which comes flying around and whatever it is. I think it is something to do with the way the laws of physics operate. Now, if the laws of physics are not computational, and I said I was going to give you an example. I think I put this slightly out of order from what I meant. I'll give you an example of something which is not computational. And these things are quite easy to, some examples are very easy to explain. I think this is one of the easiest ones, so let me say. Suppose you have a finite set of polyominoes. Now, what's a polyomino? It's, let me cover this up for the moment so as not to confuse the issue. A polyomino is one of these shapes like one of these things. That is to say, a set of equal squares stuck together to make a shape. And the problem that we're trying to address here is, can you use that particular shape to cover the plane completely? If it's an individual square, obviously you could, or a little rectangle, clearly you could. But what about shapes like these? Well, individually, none of them would, but you might have a set of such shapes. Will that set of shapes tile the plane? Well, in this case, it will. And here, I've given you an example of how it's done. Now, you might say that it would be a nice computational issue to decide whether they could tile the plane or not. And in fact, if it were true that to tile the plane, they would have to do it in a periodic way. That is to say that you form some arrangement with those shapes, and that arrangement repeats and repeats and repeats and repeats in all directions. That would be a tiling of the plane, and then that would give you an answer that would tile the plane. Now, if that was the only way you could do it, then you could make a computer decide yes or no whether a set of shapes will tile the plane. But this is an example where that's not true. If you look at it, you will, I hope you can see it, it doesn't look as though it repeats. It sort of almost repeats, but it never does. And in fact, you can't tile with these shapes and make a repeating pattern. You can only do it by a non-repeating pattern. And that's a central feature of the fact that this polyomino problem, tiling problem, these things are called polyominoes if I didn't say that before. The polyomino tiling problem is not computable. It's just a nice example of such a thing. So you can have them, and you could imagine laws of physics which were based on the tiling of a plane or something like that. That's not the laws of physics we know, but that would be the sort of thing it could be. Now, I think it's at the bottom of this one here, if you can see what's going on. What are the laws of physics as we understand them today? Well, there's Newtonian mechanics. I should make a point here that starting with Newtonian mechanics, the laws that we know depend on continuous parameters. They're not just discrete numbers. So that's a little point one has to worry about. And I worry about it sometimes, but I'm not going to worry about it here. I think it's not the central point. It could have been. I don't think it is. You can certainly approximate Newtonian laws very closely by discrete elements. That's not quite answering the question, but at least it's an indication that continuous numbers aren't something which are going to make the story different. Okay, Newtonian mechanics. What about Maxwellian electromagnetic waves, electromagnetism? Add that to Newtonian mechanics. What about relativity theory? Add general relativity theory to it. Quantum mechanics. Do they make any difference? Are they things you could put on a computer? Well, people put these things on a computer all the time. So you might say, yes, they're computational. However, there is a little problem with quantum mechanics. A little problem, well, I'm going to say it's a big problem. Let me say, I'm afraid that I have to describe what quantum mechanics is, and that's not so easy. Let me give you a rapid description of the central points. And here at the top, I have an example of two experiments, idealized experiments, where you might have a laser here emitting individual photons. And here we have a mirror. Well, it's a half-silvered mirror, what's called a beam splitter. So this photon, see a half-silver, or a beam splitter, half the light gets through, half the light is reflected. So what happens then? Well, you might say that half the number of photons get through and half of them are reflected, and we have detectors here and here. This one or this one will receive the photon, not both, not neither. And that's a particle nature of the photon being illustrated. It's behaving just like a particle. But suppose I have ordinary mirrors here and here, and another beam splitter, and I put detectors here and here. Remarkably, you find that these two routes that it might take cancel out as going upwards, and they all come this way. And that wouldn't work for individual particles, because if you had a single particle, it might go this way and this way. This one, it might go this way and this way. That means half of them will come this way, half of them will go that way. That's not true. They all go this way. And you can only understand that, really, if you think of it as a little wave. And these waves cancel each other out when they come this way, and they add up going this way. So that's the way we think about quantum mechanics. But let me say a little bit more. The way we think about quantum mechanics, you see, this is just individual particles. But here, you see, these have these different routes. And what you want to say is that the photon takes this route, and it sort of takes this route at the same time. So it does two things at once. And that's the way we think about quantum mechanics. Particles can be in two places at once. It's a crazy thought, but that crazy thought seems to be true of the way individual particles behave. And the way we think of that in quantum mechanics is that you sort of add together the two possibilities. It could do one thing, plus it could do the other thing. So your combined state is adding the two things together. And we don't just add them together, we add them together with complex numbers. A complex number is a thing with square root of -1. Don't worry about the details here. I just want to give you the general picture. so that you have these weighting factors, which are these funny numbers. You need them to do that to make the interference work and everything. But let's not worry about the details. Now this, I've used the letter U here. What does that mean? That's the Schrödinger equation, the evolution according to quantum mechanics. And the thing I want to say is that it's what's called linear. That is to say, if you have a superposition of one thing and another thing, and if one of the things would do such and such according to the equations, and if the other would do such and such according to the equations, then the superposition of the two together will be the superposition of the two results. I'll say a little bit more about that in a minute. That's what unitary evolution, or the Schrödinger equation, says. That's half of quantum mechanics. The other half is what's called making a measurement, or the reduction of the quantum state. And that's a little paradox, because quantum mechanics is a paradox with itself. It's sort of self-inconsistent. People don't usually emphasize that point. The thing is that when you make a measurement, you then say, oh, well, this superposition of two things, one of them happens or the other, and the probabilities are given by these, with a squared modulus of these complex numbers. And that's what's called R. That's the reduction of a state. That's what the thing does when you make a measurement. Now, let me go on, because I can't remember what I said at the bottom of that slide. I want to give you an illustration, leave that there, a little illustration of what quantum mechanics linearity means. Now here we have, I think I'll start with this one here. Here we have an example. There's a laser emitting, can you see that there's things which should be off screen and they're not. Here's a laser which emits an individual photon, and if it goes this way, it hits the brown thing and produces a whole lot of junk. Okay, that's one thing it might do. Suppose we put a mirror in the way, then it's reflected off the mirror, hits the green thing and produces a lot of junk. Now what quantum mechanics says is, suppose we make this a beam splitter, so it's a half silvered mirror, half the light goes through and half the light is reflected. Then whatever this does produces this junk, whatever that does produces that junk. Both these things happen together in superposition. Well, that's the way it works. Looks strange, but that's the way it works. I'll make it look even stranger in a minute, because here is an example, a sort of example that Schrödinger himself was like to do. Here we have a poor cat, which is, here's the laser again, which hits this detector, and that fires the gun and kills the cat. Now, if I have it the right one, yes, that's the right one, kills the cat. Suppose there was a mirror there, then it reflects off the mirror and the cat's alive. But suppose it was a beam splitter. Of course, that's the problem. If it's a beam splitter, then the cat is alive and dead at the same time. And Schrödinger was saying that's a load of rubbish. You see, people sometimes quote Schrödinger's cat and say, well, Schrödinger said you could have a cat which is alive and dead at the same time. What he's more saying was, no, it's just showing a weakness in our understanding of quantum mechanics. Because if you follow his equation, because it has this linear property, that means that you have to, if this beam splitter says this and this happen together, that carries right up to the level of a cat. Often people say, oh, well, that's not enough. You should worry about the environment. You should worry about the observer coming along and all that kind of stuff. Okay, well, let's worry about them to some degree. And here we have an observer, and we have an atmosphere, and here we have the mirror thing being reflected, and what happens with the beam splitter? Well, it doesn't help. It doesn't matter whether the environment's there or not. It doesn't matter whether somebody comes and looking at the cat. You might, here's the cat, the person looking at the cat, and of course one, I don't know whether you can see the difference. One has a smiling expression and the other frowning expression. And the point is that the observer seems to be in a state of confusion about seeing a live cat and a dead cat at the same time. And you might say, well, how do we know what the thought processes of the observer are? Do they satisfy quantum mechanics or something? And, well, you just look at the expression. You see that's a superposition. So there's something funny, something going wrong. Well, many people take different views on this, and one of the common views is that you have to take both of them at once, and it goes right the way up, and there are two worlds, and the cat is alive in one world and dead in the other world, and if you come and look at it, then you're in a world, whichever it is, and so on. It doesn't quite make sense, because you've got to have a world which involves Or you should have a multiverse or something where all these different things are happening. And we really want a theory which describes the world we perceive. We don't want a theory which describes all sorts of worlds we don't perceive. So it seems to me, or a world which is some kind of superposition of all these worlds. So we really need something else. Now, my own view on this is that what we need is something to do with gravity. Now, people often say gravity, well, that's ridiculously tiny. How is the effect of gravity going to make the slightest difference to most of these things? It's an incredibly weak force. That's a correct statement, but it's not a relevant argument, because the way gravity comes in is just in changing the way we look at things, not so much that its gravitational forces are relevant. It's not the forces at all. I want to remind people of the foundational fact of Einstein's general relativity, which goes back to Galileo, and you have to imagine Galileo dropping a big rock and a little rock from the Leaning Tower. Of course, he maybe never did that. It may be apocryphal. Never mind. He certainly thought about such things. And let's imagine the big rock and the little rock dropping. They drop together, as we know. Forget the air resistance, that's secondary effect, not important here. The big rock and the little rock drop at the same speed, and if you were an insect sitting on one of the rocks looking at the other one, they would seem to hover as though there were no gravitational field. So you can get rid of gravity, at least locally, by falling freely. And this is now familiar. Space travelers can be floating around in space without feeling the field of the Earth, which is sitting right there. And that Earth's gravitational field is not felt by the astronaut at all, because the astronaut is falling freely. Falling can be around the Earth in an orbit, that's fine, and doesn't feel any gravitational force. Okay, that's the principle I want to use. Now, this is a detailed argument, which I'm not going to go through here. I just want to flash it at you. If you have a quantum mechanical experiment which involved gravitation, and let's suppose this is it sitting on the table here. So the Earth's gravitational field is supposed to be taken into consideration. Now, you could do it the Newtonian way, which would say gravity is just another force, and you do the usual thing that quantum mechanics people do. They do what's called putting a term in the Hamiltonian and so on. Don't worry about what that means if you don't. It doesn't matter. But there's a standard procedure that people use, and then gravity would be like everything else, and it wouldn't cause any problems with standard quantum mechanics. But if you take Einstein's view, it's the one I just showed you with the freely falling, gets rid of gravity, then you say gravity is really just the effect of an acceleration. I mean, it's just like an acceleration, so that you use a frame of reference which falls freely under gravity, and then the gravitational field is gone. Now, this gives you two ways of looking at your experiment. And they almost come out the same. If you go through the details, you find they almost come out the same, except there's a funny thing called a phase factor, and that funny phase factor has a rather irritating term which involves the time cubed. And that's a technical point. The point is, though, that it tells you the following, that if you were doing these two different ways of doing gravity, they give you what are called two different quantum field theories. And you have to stick with one or the other. It's fine here if you only got one gravitational field, you can stick with one or the other, and that's fine. But suppose you had a gravitational field of an object. You see, this is my Schrodinger's cat. A big object which has been displaced into two places, and its gravitational field is the thing we're going to worry about. Now, this one will have a different gravitational field from that one, and since the quantum field theory is different for this one from what it is for this one, this means you're not allowed to make these superpositions. And so the superpositions are not consistent if you take the Einsteinian view for gravity. So this tells you that there's a basic conflict between Einstein's general theory of relativity, beautifully, I should say, confirmed. Quantum mechanics has an enormous number of confirmations, but so also quantum mechanics usually on a small scale in one sense or another. In gravity, it's on a large scale in one sense or another. But you want these things to come together and make sense as a theory as a whole. And what we see is that they're fighting against each other. They don't live together in the way that we normally do quantum mechanics. So my view on this, the way to get out of this problem is that this R process, which I think I have I 5 minutes, have I? This R process, which there's some trouble with this system, it's probably sitting there somewhere, which is the measurement part of quantum mechanics. You see, they've got Schrödinger equation, it chugs along until somebody makes a measurement. And then making the measurement, you violate the Schrödinger equation. Yes, it wasn't that one, sorry. Never mind. Let's not worry about it. It tells you, see, following the Schrödinger equation, you have these superpositions. So you say, this thing and this thing happen together. The rock is in this place and it's in this place at the same time. But the measurement part says, no, it's flopped to one or it's flopped to the other. And usually people say, well, somebody comes and looks at it. But I'm saying that's not the point at all. Because of what I was just saying, it happens spontaneously. It becomes one or the other. Now, that's not something that most quantum physicists will say. If you ask them, they'll go on to one of these other explanations, which I don't think work. But what I'm saying is that the correct answer is that it does spontaneously become one or the other. Now, I'll say a little bit more about that. In fact, what I was really going to say is probably not the one I have next. Yeah. I'm not even sure I have it. Never mind. You see, you can have experiments. There is currently an experiment which has been going on for about maybe a couple of decades, where you have a little tiny mirror, and this little tiny mirror is about a tenth of the thickness of a human hair. It's very, very tiny, just a little bit too small to see. And the idea is to put this little mirror into a superposition of two little slightly different places. And you can do this by hitting it with a photon, banging it 1,000,000 times with a photon, and that will be enough to displace it so that the nuclei in that little mirror are displaced a little bit away from what they were before. And you then work out a calculation from the argument that I just didn't show you, but carrying that argument to its conclusion, you deduce that this slight displacement between the two instances of that mirror will make it spontaneously become one or the other in, depending on details, seconds to minutes, something like that. This experiment is being done by Dirk Baumeister, and he's been working at it for a long time. I don't know when there will be a conclusion on that. I would be fascinated to see. And we want it to be a positive conclusion, in other words, that quantum mechanics is violated at that scale. And the scheme that Stuart Hameroff and I, the orchestrated objective reduction, does involve this idea. So I should say, when people say, isn't that scheme wild and crazy because it involves quantum mechanics in the warm, wet environment of the brain, I'm saying it's even crazier than that, because it's not that quantum mechanics has to be sustained in this warm, wet environment, and we believe it can be done in microtubules, things like that. That's the idea. That not only that you sustain this quantum coherence at that level, but that you can actually get it up to the level at which we need something new in quantum mechanics. Now, why am I talking about this reduction of the state and all that? Because this is the only place I can see where there could be a non-computable physics going on. And it's not, well, sometimes people say, well, here's a mystery and here's a mystery, they must be the same, and that's my argument, ha-ha. Well, it's not what I'm saying. I'm saying that the argument is that we need something which is different from conventional physical theory, but which is also a big enough effect that it could be relevant to what we're seeing. It's not that consciousness is some mysterious particle running around and we finally collect them in our heads or something like that. It's not that at all. It's that this process of the reduction of the state, and here is my last transparency, which I hope explains what I'm saying. This is a sort of space-time picture, and here we have a lump being put into a superposition of two places. Now, time is going this way, upwards here, and here we have a picture, you're supposed to think of that as space-time. And the gravitational field of this lump warps the space-time a bit, and you have this little channel which goes along, which follows the history of that lump. Now, if it's put into this superposition, you pull the two apart, and then you see these two channels deviating, and the space-times now don't fit together properly. Now, the argument is that in a space-time volume of order 1, in what are called Planck units. Now you see, people who work in relativity theory and quantum mechanics know what Planck units are. They're completely stupid units from the ordinary point of view, but I've got them down in the picture here. I can't read them off, but maybe you can see them. The point is that in Planck units, Planck's constant over 2 pi, the reduced Planck's constant, is put equal to 1. The gravitational constant is put equal to 1, and the speed of light is put equal to 1. You just get away with doing that. That's perfectly all right. It's just crazy units, but nevertheless. But if you use those units, it's that the measure of the space-time splitting, how much volume is there in that, is of order 1 before one of them persists and the other one dies. So this is the idea. You have a universe with a lump in one place, then it's in 2 places superposed, and then one of these dies and the other one survives. Now the point I'm making is that in current quantum mechanics, well, they don't even think about it this way, but in current quantum mechanics, this is a purely random process. What I'm saying is it's something much more subtle than that. It's something which is a non-computable process, but not necessarily, it looks random, but it's not necessarily random. And there's something which I'm referring to, Stuart and I refer to as a moment of proto-consciousness. So if you like, this is the building block in this scheme of what consciousness is made. So I'm not saying this is conscious, because it's not got any meaning to it, it's not related to other things, it's just an element of what you need to build consciousness. So the argument is that whatever consciousness is, it's a physical thing, but it's not part of the way physicists normally think about physics. It's part of the extension to current quantum mechanics that I believe is necessary, and which I hope will be revealed in experiments, and that is the building block out of which consciousness is constructed. Of course, it's a real challenge to see how this idea can actually be playing a role in, well, we presume microtubules, maybe other structures in the brain as well, in an organized way, in an orchestrated way, such as this objective reduction, that's the OR of the OR, the orchestrated objective reduction can actually be playing a role, the role that consciousness does in fact play in the way we behave. Thank you very much.